A landfill is a place to dispose of waste material by burying it and covering it over with soil, especially as a method of filling in or extending usable land. Landfills typically consist of food waste, plastics, consumer goods, and packaging. Even though these items should be disposed of elsewhere, it is inevitable that electronics, appliances, yard waste, and even hazardous waste enter these municipal waste streams. These wastes emit pollutants, of which require air pollution control. Landfills are classified according to amount and types of waste received. Today, Florida has approximately 95 active Class 1, 2, and 3 landfills. Class 1 landfills receive an average of 20 tons or more of solid waste per day, and Class 2 landfills receive an average of less than 20 tons of solid waste per day. Class 1 and 2 landfills receive general, non-hazardous household, commercial, industrial, and agricultural waste. Class 3 landfills are those which receive only yard trash, construction and demolition debris, waste tires, asbestos, carpet, cardboard, paper, glass, plastic, furniture other than appliances, or other materials approved not to produce leachate which poses a threat to public health and the environment. The municipal waste industry contributes to global contributions of greenhouse gases, as well as air pollutants that can cause direct harm to human health.
A primary concern that must be addressed in the design and operation of modern sanitary landfills is the potential explosive nature of gases that are produced by decomposing solid during the landfill's life. Landfill gas is a product of solid waste decomposition by anaerobic digestion composed primarily of methane and carbon dioxide, both of which are greenhouse gases. Oxygen, water vapor, and minute concentrations of trace gases such as nitrous oxide, hydrogen sulfide, carbon monoxide, VOCs, and non-methane organic carbons. The chemical formula for the anaerobic biological conversion of an organic solid waste to methane and carbon dioxide may be described as the decomposition of cellulose, resulting in a final composition of 50% methane and 50% carbon dioxide by volume. Methane is not harmful to human health, but when mixed with the appropriate amount of oxygen, it is flammable and can potentially be explosive, a characteristic many landfills take advantage of by converting landfill gas to energy. Human lungs transform oxygen into carbon dioxide, which is exhaled and uptaken by plants. Hydrogen sulfide at high concentrations may produce multiple health effects such as irritation to the eyes, throat, and lungs. Collecting landfill gas can improve air quality by reducing odors and emissions of pollutants such as non-methane organic carbons that can contribute to smog formation. Our task was to assess the major air pollution problems generated from landfill gas, focusing on the means to mitigate their contributions toward global greenhouse gases, effects to human health, effects of non-renewable resources and energy costs, associated regulation, and landfill air pollution control methods of the best available and most effective technologies.
Landfills and landfill gas energy projects can be subject to air quality, solid waste, and water quality regulations and permitting requirements. State and local governments typically develop their own regulations for carrying out the federal mandates. Therefore, specific requirements for construction and operating permits differ among states. It's important for project developers to review applicable requirements and regulations. The Clean Air Act, CAA, regulates emissions of pollutants to protect the environment and public health. The CAA contains 5 provisions that may affect landfill gas energy projects. 1. New source performance standards and emission guidelines. 2. National emission standards for hazardous air pollutants, NESHAP. 3. New source review permitting. 4. Title 5 permitting. And 5. Information Collection Authority, which was used to implement the Greenhouse Gas Reporting Program. Landfill gas energy projects can be part of a compliance strategy to meet EPA's landfill NESHAP. Under this rule, landfills meeting certain design capacity, age, and emissions criteria are required to collect landfill gas and to either flare it or use it for energy.
The New River facility is a Subtitle D bioreactor landfill with Title V permitting. New River Regional Landfill collects waste from a 6-county region, including yours truly Alachua County, resulting in a combined 800 tons of waste per day, peak 1,200 tons per day on special days.
Opened July 1st of 92.
The 200-acre facility is divided into 6 cells. Each undergoes an anaerobic digestion cycle to collect the waste emissions. First, Waste is placed and covered with a double-layered liner and a foot of clay.
So this is the clay, this is the cover soil. And this is what they use both to line the bottom of the landfill, and then they also use it as cover soil to prevent gas emissions.
Yeah.
You mold it, you compact it, and that's what you get your low hydraulic conductivity, or that low permeability.
Over time, these emissions are pumped, collected, and analyzed by on-site instrumentation of relative composition. A bioreactor landfill operates to rapidly transform and degrade municipal waste. The increase in waste degradation and stabilization is accomplished through the addition of liquid and air to enhance microbial processes. By efficiently designing and operating a landfill, the life of a landfill could be extended by as much as 20 years. Different techniques may be used to collect landfill gas. Possible options include use of horizontal collection systems, vertical wells, or surface trenches under the caps. Let me explain. Vertical wells are drilled either in clusters or as individual units. In addition, well spacing is variable and is generally recommended based on an evaluation of the radius of well influence. The clustered wells are completed at varying depths to get top-to-bottom aeration. Horizontal trenches or vertical wells are connected by a manifold to a mechanical blower. The blower induces a vacuum in the manifold and in the wells or trenches, extracting gas from the landfill interior. All the while, the vacuum has to be maintained in such a way so as to not draw air into the landfill.
So the two blowers that are operating are what is powering the vacuum system across the whole landfill. And so what we have are two blowers or two vacuum systems working in tandem, and then you have a backup. You always build a backup when you're balancing your well field, which is what we do on a pretty continuous basis out here. So the harder you pull, the more chance you have of pulling in air. So you're introducing oxygen into your landfill, which is something that you don't want to do.
Maintenance of the gas collection system is critical to capture quality gas in great quantity. Gas quality is an important measure of a fuel's performance and safety. Trace gas components are an important factor as well due to regulation.
For landfill gas emissions, peak concentration for stored waste climaxes at around 5 to 7 years. As a result, most air pollution control methods for Class 1 landfills are more subtle by nature and consequently not as intensive as other air pollution technologies found in other industrial services.
Well, there are many different trace gases that are present in landfill gas, but they're at such small quantities that we typically don't deal with them on a daily basis. That's something that you check on an annual basis or maybe a semi-annual basis. Typically, or on a daily basis, when we're balancing our well fields, we're dealing with methane, carbon dioxide, oxygen, and then a balance, which would be both your water vapor and your nitrogen. So when we look at all these wells, we're looking at methane and carbon dioxide and oxygen.
Landfills affected by RCRA Subtitle D are required to control gas by establishing a program to periodically check for methane emissions and prevent off-site migration.
We have 27 groundwater monitoring wells and 28 gas monitoring wells to make sure methane isn't moving off-site.
Currently, the gas is burned into the atmosphere by this flare tower. The barely visible flame is indicative of how fuel lean the emissions are.
Flare has 3 blowers to it. We use 2 at any given time, but we're able to set the flow rate of the vacuum system either by a flow rate or by a pressure. Typically, the flare operates at about anywhere from 15 or 1600 SCFM, standard cubic feet per minute. So that's what it's pulling out of the landfill at any given moment in time. But we can go up to about 1800. I think I've seen it at the complete maximum around 1850, 1900. Okay. But we don't like to operate it like that. We don't just recklessly pull in and jack up the SCFMs to as high as they can go. There's a balance that we find. Typically, or at this site, it's about 1,600. Seems to be where we can cruise pretty well. And so this is telling us right now that we're reading about 1,200 SCFM. What's the concentration of oxygen in the air? 21.
Given an ambient air concentration, 79% nitrogen, 21% oxygen, resulting exit gas concentrations for an ideal bioreactor landfill would be 79% nitrogen and 21% carbon dioxide. This assumes all oxygen is utilized for waste degradation. However, in an actual aerobic bioreactor setting, conditions include both anaerobic and aerobic processes, thus methane formation as well as carbon dioxide formation results.
And what you look for is you look for 50% methane, about 45% CO2, and then less than 1% oxygen and some water vapor and probably your nitrogen gases. As the flow rates change, we go around and rebalance the well field, and so that's what the gas emission monitor is for, is the GEM, as we call it, is to make sure that all the wells look good, because if all the wells are at 50%, then we know our flare is getting 50%. This is a gas emission meter. We call it a GEM. So what we'll do is we'll take a sample of gas right out of here and check the quantity. So we're seeing a little high on the water vapor in the balance, but we're getting 50% methane, 35% CO2. As long as we're less than 5% oxygen, we're okay. We like to see it below 2%, so it's a little higher than we'd like. We could let it run for a little bit longer and see if that changes it. But overall, we'd call that pretty good methane, pretty good landfill gas. But it's, the gas comes into here. That vacuum, or the landfill gas, is wet gas. There's water vapor in it. It flows from the sump into here. This is called a condensate knockout. Now we have baffles in here that create a surface, that allows for that water vapor to hit the surface, condenses, becomes a liquid, and then it drains out back into the bottom of the sump, and then we use pneumatic pumps to pump the condensate out, and that goes to treatment with the leachate. And so what we have is wet gas on this side, and we have dry gas on this side, and the dry gas is what gets burned. All that's going on right here is we're aerating these ponds, and that helps with the denitrification.
Yeah.
And nitrates and nitrites, ammonia to N2. The N2 goes off, and then helps reduce the nitrogen that we would otherwise recycle.
Landfills and owners of stationary combustion equipment that burns landfill gas may be required to report greenhouse gas emissions under 40 Code of Federal Regulations, CFR, Part 98.
So this is all the electrical equipment. We have both a hard copy readout of the gas flow and the temperature of the flare, and then the digital. So the engineers at Jones Evans who take care of this site see this in real time at all times, and then our guys out here see this in real time at all times. But then for DEP, we're required to maintain hard copies, and so the hard copy is kept in a safe place.
The New River Regional Landfill has the monetary capital and designs in place currently to facilitate its own waste-to-energy facility. Here is the design specs for the facility. The new waste-to-energy facility will premiere 2 generators with space in place for a third when operations expand. New River claims this energy generation will bring the facility great profits. The waste-to-energy facility and flare tower do not have to purify landfill emissions, which already contain 50% methane. Hypothetically, if the facility decided to sell its fuel commercially, the effluent would need to be stripped of water vapor and carbon dioxide to produce a 98% pure methane stream.
It's only 50% methane, so if you're going to put this into a natural gas pipeline, you have to strip all the CO2, all the water vapor off of it. You have to make it something that's 98% methane. There's hydrogen sulfide in there too, so you remove that. If you're just burning it to create energy on site using a generator, you don't necessarily need to do that. You could just burn it as a landfill gas. And there are generators that can do that. And so it totally depends on your application, what you're doing.
Gas recovery and subsequent use play an important role in reducing the total cost of anaerobic bioreactor landfills. The estimated capital required for a 40-acre collection system designed for 600 cubic feet per minute of landfill gas is approximately $1,022,000, or $25,550 per acre, assuming one well is installed per acre. Typical annual operation and maintenance costs for collection systems are estimated to be $180,000 or $4,500 per acre. If a landfill gas energy project generates electricity, often a landfill will use a portion of the electricity generated to operate the system and sell the rest to the grid to offset these operational costs. Flaring costs have been incorporated into these estimated capital and operating costs of landfill gas collection systems because excess gas may need to be flared at any time, even if an energy generation system is installed.
Increased gas creation is the motive for the collection of the landfill emissions as fuel source, since it's carbon-rich. Injecting lime slurry as well as the fly ash act as a pollution measure to control methane formation and inhibiting gas formation outright through methanogenesis. There are technologies exist for observing and recording emissions data. Lysimeters is one of the examples for measuring the evapotranspiration of waste and consequently its moisture contents.
Team GatOhZONE would like to thank those at New Rivers Regional Facility for allowing us to tour their site to aid in our research.
I'm gonna be in the blooper.
You guys learn in Dr. Wu's class about height of the stack?
Yeah.
Yeah.
That impacts local air conditioning. So it's not quite the same thing, but we don't put the flare down here.
Yeah.
We put it a little way down. It's a hell of a thing to smell once you take the lid off.
Oh, I can only imagine. If you were to try to describe it, what does it smell like?
Stinky.
Like burnt diapers?
No. It's if you can imagine garbage that's several weeks old.
Sour milk.
Sour milk.
Oh, it's like sour milk, huh? Oh, dear.
Have you ever been to Balls?
Yes. Oh, it smells like balls. It smells like cheap beer and sweat. I see.
Really, it smells like sour milk is the best way to describe it.
That was rich.
No. So, see over there by in the corners?
Yeah.
There's a couple fires.
Okay.
Make sure that your gas collection system and your flare is operating effectively.
That's right. We got trash up in here.
Don't be talking trash. Don't be talking trash.
I only heard that one 30 million times.
Oh, dang. That was original.
I liked it. You're a star, June. You're gonna be a star. This all used to be trash that was standing on.
Still is.
Still is. Yeah. So these shoes are gonna smell forever. Is that what you're trying to tell me?
Once you clean them.
Oh my god. Oh, there's a lot of sludge. GatOhZONE? Oh, we should make a gang sign for GatOhZONE. Oh man. That would have been a dope idea.
Peace out.
I can't believe it.